Hello students, welcome to the session from Infinity Learn NEET channel. This is Suresh, Faculty of Chemistry. Today we are going to discuss about short tricks in solutions and colligative properties. In the solutions and colligative properties, definitely you are going to expect one sure shot question from NEET examination based on NCERT, and let us talk about what are the major topics that are involved in solutions and colligative properties. There you can expect a question from concentration terms like molarity, normality, molality and mole fraction, and also Henry's law, then Raoult's law, and ideal and non-ideal solutions, and colligative properties, relative lowering of vapor pressure, elevation in boiling point and depression in freezing point, and osmotic pressure. At the end we are going to see the Hoff factor, abnormal molecular masses. So we will start with molarity. Is one of the concentration terms we regularly use. This is the number of moles of solute present in a liter of solution, and it is calculated based on m is equal to weight of the solute by gram molecular weight into 1000 by V expressed in milliliters. And you can go with various combinations like dilutions and additions and mixtures and all. And we can see the molality. Whereas you see the molarity, it is temperature dependent. Molarity is going to be temperature dependent. Whereas when the solution is diluted, on dilution, it is going to be M1 V1 is equal to M2 V2. This is the dilution law where M1 V1 is the molarity and volume before dilution, and M2 V2 is the molarity after dilution. When the solution is mixed, the molarity of the mixture is equal to M1 V1 plus M2 V2 upon V1 plus V2. And also you can see the molality, it is temperature, molality, weight by gram molecular weight into 1000 by weight of the solvent. Number of moles of solute present in a kg of solvent is called as a molality, and molality is most preferred as this is temperature independent. And you can see which of the following concentration term is temperature dependent and temperature independent. Definitely you can get a question from the NEET examination based on this criteria. When it comes to all properties, you are going to say molality and mole fraction is temperature independent, and it is mole fraction, it is the ratio of the number of moles of a solute to the total number of moles is called as the mole fraction. Let us say A is a component and B is another component. It is a binary solution. The mole fraction of A is given as Na upon Na plus Nb. Similarly, for the component B, the mole fraction is going to be Nb upon Na plus Nb, and the sum of these two is going to be equal to 1, and it is also temperature independent. Talking about the normality, normality is the number of gram equivalents present in a liter of a solution. It is just like molarity. In molarity you have taken the number of moles, whereas here number of gram equivalents you have to consider, and there is a term called gram equivalent weight. We have to check how to do this. And similar to that normality and molarity for dilution. For normality, for the dilution, it is equal to N1 V1 is equal to N2 V2. For mixing, this normality of the mixing is equal to N1 V1 plus N2 V2 upon V1 plus V2. And what is the relation between the normality and molarity? You can see this gram equivalent weight can be taken as gram molecular weight upon N factor. Gram equivalent weight is equal to gram molecular weight upon N factor. And how to calculate that N factor? That N factor could be, you can see, for an acid, the number of acid, the N is going to be the number of H plus ions that can be donated by one molecule of an acid, that is what you call it as the basicity. For the base, it is going to be normality is equal to molarity into acidity of the base. I mean to say N factor is going to be number of OH minus ion that is donated by one molecule of a base. I mean to say the relation between normality and molarity, normality is equal to molarity into N factor. That is what you call it as a valence factor. What if a salt is given? You have to take the magnitude total charge on either cation or anion is going to be your N factor. For an oxidant or a reductant, you have to say the number of electrons that are involved in the redox change is the N factor. So, it is normality is also temperature dependent. Talking about the next one, the relation between the molarity and the mole fraction. The molarity is equal to mole fraction of the solute into 1000 into density upon mole fraction of the solvent and Ma and Mb, and this is mole fraction of the solute and this is mole fraction of the solvent, and it is going to be the molecular weight of the solvent and it is going to be the molecular weight of the solute. This relation is a simple trick to understand the relation between the molarity and mole fraction. Moving ahead, the methods of concentration terms, when the weight and percentages are given, you can calculate the molarity. Molarity is equal to 10 into density into weight percentage upon gram molecular mass, and this expression can give you very good number of questions from the concentration terms in the NEET examination. And you can see the molality and the molarity relation. It is also very important. Molality is equal to molarity upon density minus molarity into molecular mass of the solvent. Stay always A is a solvent and B is a solute. Talking about Henry's law, when the gas dissolves in a liquid, as the pressure of the gas increases, the solubility of the gas in the liquid increases. That is what you call the effect of pressure. It is explained by Henry's law. It says the pressure of the gas is directly proportional to the mole fraction of the gas, and pressure of the gas is equal to Henry's law constant and the mole fraction of the gas. Here Kh, what do you call it as? Henry's law constant. According to this, it is a constant for a gas at a constant temperature. This is very, very important. If the gas is changed, its Henry's law constant is going to be changed. For a given gas, as the temperature is changed, it is going to change. And I want to say, for a given gas, as Kh value is increased, solubility decreases. So, this is a simple trick that you can understand from this Henry's law. Mind it, based on that, a group of Henry's law constant values are given for the different gases. You can say which gas is going to be more soluble. The gas which is having the least Kh value is going to be the most stable, most soluble gas. And Kh increases with increase in temperature, therefore solubility decreases. Talking about Raoult's law, when a liquid A and liquid B is mixed, it is going to form a solution. When this solution is formed, it is going to have the pressure, and the pressure is going to be the partial pressure of A and partial pressure of B are included, and the partial pressure of a liquid component is directly proportional to its mole fraction. That is what is said to be Henry's law. Here say Pa is a partial pressure of the gas A and mole fraction of A, and P naught A is the partial pressure of the pure liquid A, and also for the Pb is given, Pb is equal to mole fraction of B and P naught B. According to Dalton's law, P total is equal to Pa and Pb when you sum these two, you are going to get Pa and mole fraction of A, P naught B, mole fraction of B. You can also say the P total is equal to P naught A and mole fraction of A plus P naught B and mole fraction of B. And this particular partial pressure relation is what you call it as Raoult's law, and this Raoult's law is obeyed by the solutions. Such solutions are called ideal solution, and that ideal solution should obey this graph. This graph says the ideal solution behavior for an ideal solution. Mind it, the simple trick I want to say, when component A is interacting with A and component B is interacting with B before they are mixed, when component A is interacting with B, this is after mixing. The magnitude of the intermolecular forces is same. That is the simplest trick in order to show the Raoult's law, and it is an ideal solution behavior. For ideal solution, Pa is equal to P naught A, mole fraction of A, Pb is equal to P naught B, mole fraction of B, P total is equal to P naught A, mole fraction of A plus P naught B, mole fraction of B, and it gives the line like this. And intermolecular forces are same. Intermolecular forces before mixing is equal to intermolecular forces after mixing. Therefore, enthalpy of the mixing is going to be 0 and change in the volume is going to be 0. So, there is no heat loss, there is no volume change. So, these are the criteria that has to be followed for the ideal solution. Which of the following is true for an ideal solution? These are the various conditions, and this is the graph. Talking about a real solution which deviates from the ideal behavior, that is what you call it as a positive deviation. It could be negative deviation. Let us talk about the positive deviation. For the positive deviation, it is supposed to be a straight line, but it is coming up. Vapor pressure of the solution increases. Why? Intermolecular forces after mixing, it is increased. So, I want to say intermolecular forces between A and A and B and B and A and B. So, when the components are mixed, intermolecular forces are decreased. As intermolecular forces are decreased, there is a less intermolecular forces between A and B, so that component is going to be evaporated. I just want to say, I will say here it is volume is going to be, vapor pressure of the solution is going to be increased. That is what you call it as a positive deviation. Talking about the negative deviation, intermolecular forces are increased, therefore vapor pressure of the solution is decreased. That is the key point. Intermolecular forces is going to be increased. I mean to say A to A interaction, B to B interaction and A and B interaction. So, as intermolecular forces are increased, it is going to decrease the tendency to evaporate, so that vapor pressure is decreased. Therefore, you can say the downward trend in the vapor pressure. Moving ahead, how to calculate the vapor phase vapor pressure mole fractions. Pa is equal to, from the Dalton's law, YAPT, Ya is the mole fraction in the vapor phase, and Pb is equal to YBPT, and Yb is the mole fraction of B in the vapor phase. That you can say Yb gives the mole fraction in the vapor phase and Xb gives the mole fraction in the liquid phase, where X is in the liquid phase, Y is in the vapor phase. Talking about colligative properties, those liquid properties for the dilute solution which depends only on the solute number of moles or molecules, but independent on the chemical nature of the solute, such properties are called colligative properties, and these colligative properties are 4 colligative properties related to lowering of vapor pressure and elevation in boiling point and depression in freezing point and at last osmotic pressure. Definitely you can get a question from here. So let us talk about RLVP, relative lowering of vapor pressure. When a solute is added, a non-volatile solute is added, the solution vapor pressure is going to be decreased. That is what you call it as vapor pressure lowering with respect to the solute. Solvent is called as relative lowering of vapor pressure, and this is equal to the mole fraction. I just want to say relative lowering of vapor pressure is equal to mole fraction of the solute. So from this you can calculate the molecular mass of the solute. How we calculate? We can say P naught minus Ps is the lowering of vapor pressure upon P naught is the relative lowering of vapor pressure is equal to number of moles of solute upon number of moles of solvent. So why the solute is ignored? For a dilute solutions, solute number of moles is very less as compared to the solvent, so you can ignore it. From there you can say weight of the solute upon molecular weight of the solute into molecular weight of the solvent into weight of the solvent. So from there you can calculate, from this relation you can calculate the molecular weight of the solute. Moving ahead, depression in freezing point and elevation in boiling point. So in the elevation in boiling point, the boiling point of the solution is the temperature at which the vapor pressure of the solution is equal to the atmospheric pressure. Let us say this is your boiling point of the solvent and this is the vapor pressure curve for the solution. So vapor pressure always for the solution is lower than its corresponding solvent. So when you talk about at 1 atmosphere, this is the temperature at the solvent is boiling, and this is the temperature at the solution is boiling, and the difference between these two is what you call it as the vapor boiling point of the solution. Tb is directly proportional to molality, and you can say delta Tb is equal to Kb into molality. You know the formula for the molality. From there you can calculate the molecular mass of the solute. Mind it, calculation of the molecular mass from the colligative property is the important point for this NEET examination. You can see delta Tb is the difference between these two. So that Tbs minus Tb naught is equal to Kb, that is ubuloscopic constant or molar elevation constant, that is Wb upon Mb into 1000 upon Wa in the grams. So from there you can calculate the molecular mass of the solute, and also depression in freezing point, and the freezing point is the temperature at which the liquid vapor pressure is equal to its solid vapor pressure. So for the solvent the vapor pressure is going to be here. So this is the temperature at the liquid, pure liquid is freezing, and this is the temperature at the solution is going to be freezing. The difference is going to be delta Tf, that is what you call a decrease in the vapor pressure. So that is what you call it as depression in the freezing point. So delta Tf is directly again proportional to the molality. Delta Tf is equal to Kf into molality. Kf is what you call it as a cryoscopic constant. It is the depression in the freezing point when 1 mole of the solute is dissolved in a kg of the solution. So from there also you can calculate the molecular mass. So delta Tf is equal to Tf naught minus Tfs is equal to Kf into Wb by Mb into 1000 by Wa. So from there you can calculate molecular mass of the solute. So simple tricks I just want to give you, not in detailed but on the superficial. You are going to get a chance for getting every question from this kind of formulas, children. And also osmotic pressure. So, what happened during osmosis? Osmosis can happen when semi-permeable membrane is separated with two solutions of C1 and C2. As concentration of C2 is greater than concentration of C1, then a solvent is going to move from lower concentration to higher concentration. That phenomena is called as the osmosis. During osmosis, the pressure exerted to oppose the inflow of the solvent is called as osmotic pressure, where the osmotic pressure is explained by Hoff. According to Hoff, a very dilute solution behave like an ideal gas, so that you can use PV is equal to nRT, which is ideal gas equation. The same equation can be used for your dilute solution. So, P is a pressure of an ideal gas. For the solution, you can keep P as a pi as osmotic pressure. So, pi is an osmotic pressure that can be given as pi is equal to CRT, or pi is equal to N by VRT, or pi V is equal to nRT. So, here R value is 0.0821 liter atmosphere mole inverse and Kelvin inverse. So, this is a very important formula for the osmotic pressure. And also we can see abnormal molecular mass. So, for what reason we are studying the colligative properties? Colligative properties can be studied for calculating the molecular masses, but when the solute is dissolved in the solution, what happens? It may associate or it may get dissociated. That is the reason why these colligative properties gives the different molecular masses, that is abnormal molecular masses, that can be rectified by using Van Hoff factor. So, what I mean to say, the Van Hoff factor is the ratio of the observed colligative property upon calculated colligative property. That can be given by association in terms of dissociation. So, I value that is equal to normal molecular mass and abnormal molecular mass, or I value is calculated molecular mass of a solute upon observed molecular mass, or also you can say I is equal to total number of moles particles after or before after dissociation or association upon number of moles of the particles which is actually dissolved. What I mean to say here, if a solution is dissociated or ionized, the N value is greater than 1. If it is associated, N value is going to be 1, and if there is no association, dissociation, it is going to be 1. And I want to say that degree of ionization alpha is related as, for degree of ionization, alpha is equal to I minus 1 by N minus 1, that is for dissociation. If the solute is getting associated, alpha is equal to I minus 1 upon 1 by N minus 1, where N is the number of particles, or the number of particles that are after dissociation. And also relative lowering of vapor pressure, we have to take this I value and correct this colligative property. Relative lowering of vapor pressure is equal to I into mole fraction of the solute, and also you can say degree of depression in freezing point delta Tf is equal to IKF into molality, and also elevation in boiling point delta Tb is equal to I into Kb into molality, and osmotic pressure pi is equal to ICST. So, every colligative property has to be multiplied with Van Hoff factor I, that is a simple trick. And in case of dissociation, alpha value is always greater than 1. In case of association, alpha value is less than 1. In case no association and dissociation, alpha value is I value is going to be 1. And also I just want to give you a simple trick for the NEET examination at the end, trick in colligative property. So, in the NEET examination you will be asked which of the following has the high vapor pressure, which of the following has the high boiling point, which of the following has high vapor pressure, which of the following has high osmotic pressure. As number of particles increases, Van Hoff factor I value increases. Yes, based on that I can say as I value increases, boiling point increases, as I value increases, osmotic pressure increases, as I value increases, vapor pressure decreases, as I value increases, you can say freezing point decreases. So, simple things you can say, number of particles, how it is increases and how it is decreases. Say, I want to take a simple example before I complete the class. You can say NaCl, magnesium chloride and aluminum trichloride, assume there is a 100% ionization. So, you can say this I value is going to be for this I value is going to be 2, I value is going to be 3, I value is going to be 4. Based on that, you can say the boiling point NaCl is less than magnesium chloride, less than aluminum trichloride, and also osmotic pressure follows the same. Talking about vapor pressure and the freezing point follows the reverse. NaCl is greater than magnesium chloride is greater than aluminum trichloride. Like that, a simple application that you can do from the tricks from the colligative properties, and most of the times this category of questions can be easily asked by giving a various combination of compounds. So, hope you enjoyed today's class, and please like and share and subscribe this Infinity Learn NEET channel. Thank you very much.